Hi, my name is Tarishini and today I'm going to present about mathematical model for investigating the adaptive divergence of whitefish in FENNOSCANDIA. Okay, let's go with the introductions of this title. What makes these processes extremely complex and difficult to understand is that different evolutionary and ecological factors controlling the dynamics act simultaneously and often have opposing effects. The complexity of speciation processes implies that mathematical modeling can potentially play a very important role in uncovering its general rules and patterns. By now, an impressive array of models and modeling techniques that shed light on the conditions, probability, waiting time to, and duration of speciation. Models also explain the effects of different parameters and factors. These different mobs of whitefish show habitat-specific patterns in their resource use, body size, gill rake number, and life history traits. Beside historical contingency, ecological opportunity mediated by interactions such as resource competition and predation may play an important role in diversification of whitefishes with regard to ecomorphology and life history. The goal here is to use individual-based simulations to better understand condition for and various factors such as abiotic and biotic, controlling the divergence of FENNOSCANDIan whitefish into three principal habitats of subaquatic lakes. Our particular focus will be on the effects of selection for local adaptation, gene flow, carrying capacities of the habitat, and predation. Now I'm going to present about literature review. In environment, each lake has three different ecological niches which is called as habitat, which are known as littoral, pelagic, and profundal with its own whitefish population. Each lake can have up to 4 predator species feeding on whitefish, which are pike, perch, burbot, and brown trout. In individual whitefish, each individual is identified by 3 phenotypic traits, which are size, the number of gill rakers, and whether it is sexually mature or not. In selection, the whitefish population is subject to density-dependent viability selections due to intraspecific competition, habitat-specific stabilizing selection on number of gill rakers, size-dependent mortality due to predation, as well as fertility selection due to body size differences and maturation rate. In condition, the number of gill raker controls the availability of food to fish in a given environment. Other than that, in density-dependent selection, the population is subject to density-dependent mortality with survival rate of individuals with gill rakers and of size in each. In predation, the maximum gap of a predator controls the sizes and shapes of prey that can be eaten. While in dispersal, every year after the reproduction, each fish chooses the ecological niche to go to with probabilities proportional to their overall survival in each niche as accounting for both predation and density-dependent selection. In reproduction, mating is assortative by the niche and the size, while in life cycle, it begins with random death of eggs which is followed by density-dependent survival and by predation mortality. Now I'm going to present about methodology. 2 scenarios of diversification differing in initial conditions are simulated. The colonization L scenario is reflecting the current view of the post-glacial colonization of lakes by large littoral fishes, while the colonization G scenario is same as colonization L scenario, but all the initial colonizers are assumed to grow bigger by reach the giant stage. The initial population harbors genetic and phenotypic variation in both scenarios. The standard deviation of the gill raker number is 5, which is close to the values observed in natural population. The number of different morphs were imaging is evaluated and are maintained in the lake. The predation intensity is varied in the numerical simulations beside the initial condition. The predation intensity is set at 0%, 30% and 50% for each of the 4 predators specifically. The strength of stabilizing selection is measured by the value of parameter by set to 4, which corresponds to relatively strong selection. The fertility parameters are set to B1 is equal to 4, B2 is equal to 16, B3 is equal to 64 respectively in the model and following an exponential relationship with the length. These numbers were interpreted not as an actual number of eggs produced by a fish, but as a number of offspring surviving to the moment when they are subject to selection. The available data assuming were used to estimate carrying capacities that extend fish adapted to the environment where they have the optimal number of gill rakers and reach maturation at a proper size. Extant fish in 3 niches were assumed that they are reproductively isolated and fertility is a function of the female size. Among different lakes, the carrying capacities of different niches differ. The carrying capacity of the profundal niche is the particular important factor affecting the likelihood of diversification, where it varies due to the size of the lake, its shape, and the nutrient deposition rate. To interpret the numerical simulations, a given niche has been colonized successfully where the population of newborn has number of gill rakers adapted to their niche and mostly grow to a size which characterized the niche in real lakes. Let's look at the results. Table 1 and Table 2 are the results on the condition under which each niche was colonized and by how many morphs. The majority of lakes fall into 4 different compositions of morphs present, such as littoral morphs only, pelagic morph only, littoral and pelagic morphs, and all 3 morphs present. Survival of littoral morph with no other morphs emerging was the most common outcome in the simulations. It typically required the presence of predation by trout. In FENNOSCANDIA, lakes with only the littoral morphs are common. In the 2 morphs, the maintenance of the littoral morph and the emergence of the pelagic morph was the frequent outcome in both colonization scenarios for about 40%. When the trout predation was absent or small, this outcome occurs more often. In addition, in the single pelagic morph, the outcome implies the extinction of the littoral morph after it gives rise to the pelagic morph. This outcome was observed in both colonization scenarios under high predation by pike and perch, but much more common in the colonization G scenario. In the 3 morphs, the cases were very rare in the simulation as 5 cases only in Table 1, while no cases in Table 2. Colonization L scenario under large carrying capacity for the profundal niche in the Table 1, when the predation from the pike and perch was strong, but that from trout and barbot was weak. Finally, the conclusion. Overall, the modeling supported the possibilities of divergence to 3 lake habitats during the post-glacial time frame, although such cases were rare and required a large profundal habitat without predators. Divergence to pelagic and littoral morphs was much more frequent and occurred with various levels of predation. The modeling effort indicated how little actually we know about reproductive isolation mechanism as well as about habitat-specific carrying capacities and essential population dynamic parameters such as age-specific mortality in whitefish. Nevertheless, it would be interesting to apply the modeling approach to a true deep water species such as lake biculcotus and various members of Salvelinus in very large lakes using species-specific parameters. Recent empirical studies have highlighted the important role of deep water habitats which have been previously neglected in monitoring efforts. In these respects, mathematical modeling could provide an efficient predictive tool for finding new lakes with 3 morphs as well as identification of key factors contributing to their disappearance from the post-glacial lakes. Thank you.